everyone for coming. My name is Felipe. I work for Nutanix on the engineering of our hypervisor product called HV, which is based on Qemu and KVM. I'm here with Jim.
Yeah, my name is Jim Harris. I'm a software architect at Intel focused on the storage performance development kit.
And we'll be talking about vhost-user-scsi, which, as you might have heard from other talks, is a mechanism to offload the data path of a virtio-scsi device to user space. We have a little disclaimer for you to read. You can do that later. If that's not enough for you, we have another one. I think that basically just is, don't buy our products based on what you're seeing here, and we're not committed to release any of that. So just to get us warmed up and started, I wanted to begin by reviewing a typical virtio-scsi data path on Qemu KVM. That's how we've been using it until recently. There are other ways of configuring Qemu to behave, but you've probably seen very similar diagrams to that when you have your hardware in the bottom there. And then you have a host running a KVM accelerator on the kernel. And Qemu uses space with all of its threads for vCPUs and device emulation. And then you have a virtual hardware abstraction, and on the top your virtual machine with some sort of storage workload driving the device via a virtio-scsi driver. So the idea is that a virtio-scsi driver first places a request in a memory somewhere, populating the controller's VQs, and then sends a kick, right? That kick is strapped by the KVM module and delivered to Qemu via an event file descriptor. So Qemu looks at the file descriptor and knows which queue that came from, and it can go on the guest memory and pick those requests from that queue, and then submit it to the corresponding backend. So on the VM on your left there, that could be a network card with some sort of NBD or NFS backend. On the other one, it's a disk. It could be a QCal file or a raw disk over a logical volume partition, for example. And once this request completes, then it populates the response structures on those VQs, and it notifies the guest via an interrupt, which again, it's usually a file descriptor that it writes to KVM, and KVM delivers the interrupt. So with this model in mind, the motivation we had for this work was to address certain limitations that we noticed there. And the key one is basically this concept that we have this one-to-one mapping between a VM and a host process that handle the VQs. And we've been talking a lot about using perhaps multiple processes, etc. But the key thing is that none of these models give you a way of having a single process managing multiple VMs. And that's something you can do if you can offload the data path with the technology like vhost-user. Because you cannot have a single process handling multiple VMs, you also cannot effectively poll on multiple VMs. So if you want to get rid of the interrupt model and have a process spinning on all of these VMs, you cannot do that. And you cannot do that efficiently. Obviously, you could still have each Qemu spinning, but then you're going to burn a core per VM, which is obviously too much. And with a single process, you can do that by spinning on a single process, right? And it also, because of this, it becomes non-trivial to virtualize a single NVMe device in user space using technologies like SPDK, which Jim will talk about later. So the solution for that is to create this offloading mechanism. And a precedence for that is vhost-user-net, which did pretty much the same thing for networking with OVS and the PDK. So if we go back to this diagram, this would basically look like replacing this main loop with this vhost-user application. This would be in its simplest form. So you could have another process which is not Qemu handling the I/O. Ideally, for performance reasons, you probably want to have a single process managing multiple VMs in a model like that. It would work like this. So the trade-offs is pretty much where we're trying to achieve better performance, right? And in terms of benefits, it becomes, for instance, easier to implement multi-queue using multiple threads. So that's being pursued inside Qemu now with data plane and multiple threads, but it's been in the works for a while. It's been proven to be challenging due to various things like all the locks that Qemu has in place for the I/O path. It's also easier to do batching. So this is something that sometimes is overlooked. But one thing you can do with this model is also collect requests from multiple VQs and then submit them in one go. Even if you're not using SPDK, you could still think of a single write operation to a socket or a single I/O submit from different threads, right? And obviously the polling angle, which is interesting, and that will be if you have a single process, then again, looking at all those VQs, you can check if a VQ has requests in nanoseconds. So you can realistically look at hundreds of VQs in a host very, very quickly, right? There are a few drawbacks to that. One that's very important to note is if you're going to be using a single process to handle multiple VMs is a security angle, right? So if you have a bug in your or your data structures handling routines, and one guest attacks your process and cracks into it, then you will be exposing all of the other VQs, which is obviously a bad thing, and you have to be creative to find ways around that. The other is the stability. So also, denial of service is a concern. If you have a bug that crashes your process, you probably should start thinking about ways of restarting this process and having the QEMUs reconnect somehow. If you have a single process, then this is probably not very different than what you have today. Another key difference between that, and that's important to mention because it's different from vhost-user-scsi, which is what you have in the kernel, is that this vhost-user-scsi implementations, they are no longer aware of the LUNs. So all the QEMU knows about is the controller itself that it's virtualizing to the guest. And it doesn't know which targets or LUNs are attached to that controller. And that means that if you want to plug disks or manage disk hot plug, etc., you have to do that outside of QEMU. And libvirt is obviously completely unaware of what your potential target application will look like. So you cannot use libvirt for that either. We've been thinking about extending libvirt to have some sort of plugging mechanism so that you can write your own plugins and then you can use the same interface through libvirt to add and remove disks, etc. Or resize disks, for example. And finally, that's pretty obvious, you lose all of the QEMU block layer features, if that's something you rely on. Probably if you're pursuing a technology like this, you're not going to be using that anyway. So that's not so much of a problem. So if you put what vhost-user and vhost side by side look like, at the time where you're starting your process on the VM on the left, on your left, you will already have this vhost-user-scsi or VOOS application in user space there next to QEMU. In contrast with vhost-scsi, which you have on the right, and that's the module on the corner of the screen there on the kernel side. So as far as the guest is concerned, the Vernier Scale device is identical. You will do part of its initialization, like allocating these VQs, and then telling the device where the VQs are via the PCI config space. And then here's where the differences begin. So on the vhost-user case, QEMU has a Unix socket with your application, and then it sends various messages to this application, including things like the guest memory is this file descriptor, which you can map, and the VQs are these addresses, and they have these sizes, and here are your file descriptors for kicking and receiving kicks and delivering interrupts to the guest. And on the kernel side of things, this works via an I/O control interface. And I'll mention there's a few differences between these two processes that I think in the first design may have been overlooked. And now that people are using them more actively, they're noticing some issues with that. But the idea is you send an I/O control and you send pretty much the same set of messages, and then you can start your device handling tasks and queues in the kernel. So some of the important highlights here is that in terms of implementation, Paolo asked that we did a small refactor, or Stefan, I don't remember actually, asked that we did a small refactor, Paolo left, I don't know, of the vhost-scsi inside QEMU. So we split vhost-scsi into a vhost-scsi common and a vhost-scsi, vhost-scsi common obviously being the parent. And then we introduced the vhost-user-scsi underneath that as a sibling to the vhost-scsi. In terms of live migration, it's actually quite straightforward. The first patches had support for that, and At the time the patches got merged, unfortunately there were some other changes, and then the live migration handlers were dropped. But we'll probably re-add this soon, and it's quite straightforward. What you need to do is make sure your tool stack starts your target application on the receiving side, right, before you begin migrating, or have some sort of wrapper script that would do that for you. And that trick to QS the device is to use the get ring base vhost message. And what that message does is basically it's Qemu asking the device, which could be vhost-scsi in the kernel or even vhost-net, asking the device basically, where are you on the avail ring, like which position you are. And he uses that to send that over the migration stream to the other side to say you have to continue from there. So obviously when you get this message, your device needs to stop picking up requests from the ring because the index is going to be used. And what you do at that point is just you QS the device or that particular VQ where the message came in for. One thing pending for migration is throttling. So that's still pending, and it's not specific to SCSI. I think it's a generic vhost-user thing, which basically is when you're live migrating and you're trying to converge a migration, you might want to start throttling your CPUs. So the gas slows down on how much memory it's dirtying. And there is no mechanism in place that I know of to tell the device to throttle as well. So not on the vhost side. And that means that the device itself can continue to dirty memory at a very, very high rate. The interesting thing to note as well, as more people start to use this and develop vhost and vhost-user devices, is you might start finding other areas like this for improvement and perhaps some bugs. We picked a couple which are generic to vhost during this work. And as I mentioned, there is a key difference between vhost and vhost-user, which is the fact that the Unix socket messages that are sent, they are asynchronous. And the I/O controls that are used to derive vhost in the kernel message, they are not. The I/O control blocks until the kernel module is done. And the reason this is tricky is imagine Qemu is telling the device that some memory was hot plugged. So if you do an I/O control and you say some memory is being hot plugged, you know that when the I/O control return, the device has completely finished mapping that new memory into its own space. And if this is a Unix socket message, then you can tell your device there's a new file descriptor here with a new memory region on this VM. And what happens is that Qemu sends this message and then tells the guest to carry on executing with its new memory. But your device may not have finished mapping that yet. So during this work, one of the things we did is introduce a new feature for the vhost-user protocol, which is called reply ACK. And the idea is that for certain messages, you can tick that flag, and that causes Qemu to wait for you to reply to a message that previously, or in the original protocol specification, didn't really expect responses. Prina's not in there. She was the one who did that work. Cool. And with that, I'll pass on to Jim to start talking about such a target application example using SPDK.
Okay, thanks, Felipe. Okay, so first I just want to give a little bit of a background on SPDK and what it is before I start getting into details on our vhost-user-scsi implementation. So SPDK is basically a set of software building blocks. It really started out with a pulled mode NVMe driver, kind of taking what DPDK did for networking and applying that to a storage context with NVMe. There's a number of other drivers and libraries and applications that have been built on that now, and they're all based around storage. So storage networking, and now storage virtualization as well. SPDK primarily leverages DPDK. That's our default environment. We do that for things like memory management, PCI device enumeration. We have some abstractions for people who maybe want to use libraries without using DPDK, but primarily we're using DPDK. In fact, early on when we started this project, it was actually called DPDK for storage. The project was started internally at Intel about 4 years ago. 2015, it was open sourced. It's BSD licensed, and you can get more details on the spdk.io website. So next, this is a little bit of an eye chart. This is just kind of showing some of the different building blocks that SPDK has. Today, I'm going to mostly be focusing on the vhost-user-scsi target, the pull mode NVMe driver, and then I'm going to talk a little bit about our logical volumes implementation and how we use that for sharing SSDs. Okay, so basic architecture. So you see we've got an NVMe SSD there. When you start configuring this, we basically have a JSON RPC interface with SPDK for configuration. So when you're going to set up a vhost-scsi, so first, whenever I say vhost-scsi here, this means vhost-user-scsi. We're not talking anything kernel here, just to make sure that that's clear. I was a little bit lazy. I didn't want to type out the user part and all these boxes. So it's going to create all these SPDK constructs for the vhost device, in this case a vhost-scsi controller, and the backing storage. And then, like Felipe mentioned earlier, we create this domain socket, which we create per vhost-scsi controller. So as you start building more and more of these controllers for more and more VMs, each one's going to have their domain socket, and connecting to that domain socket is basically how that VM gets access to their storage. Okay, so now it's been configured. The VM is now going to attach. So Qemu connects to the domain socket, starts passing vhost messages to give SPDK information. Again, like Felipe was talking about, where's the memory, information about the queues, etc. And so then SPDK gets started here. So you'll see here, here we just got 2 logical cores. It can be set up on multiple logical cores. So first, for load balancing from a performance perspective, we're going to pick a logical core to run these pollers on. And so first we're going to start a vhost-scsi poller. And it's basically, I'm going to get into a little bit detail later about how exactly this works, but it's just going to pull the vert queues that are associated with that vhost-scsi controller. And then for NVMe, so NVMe has a really nice protocol. For those that aren't familiar, you can allocate queue pairs, which are completely independent of one another. So at this point, we're going to allocate an NVMe queue pair, and we're going to set up a poller for that queue pair as well. And then we're going to repeat this for additional VMs. So configuration tool is going to set up these SPDK SCSI structures for other VMs, and as they get connected, we're going to start these pollers across other cores. Okay, so next, a little bit about polling. So, polling, there's a couple different ways to do polling. In some cases, it's, synchronous polling, where you submit an I/O, you poll until that I/O is complete. Everything with SPDK, though, is completely asynchronous, non-blocking. So effectively, what we have with SPDK is a little thing we call a reactor running in each L core, and it's effectively just a little mini scheduler. With SPDK, we're going to take these cores, and it's the only thing that's going to run on these physical cores on the system. And this reactor is basically just going to iterate through these pollers round robin. This is actually pretty effective because when you look at the cost of checking when a vert queue has new I/O to do, or checking when an NVMe device has posted completions, it's really, really cheap. On Intel Xeon processors, you have DDIO, so when an NVMe device posts a completion, that completion entry is going to be in LLC, and so it's super cheap to go check and see when that has been updated. And so this ends up kind of working a little bit like a ping-pong type operation. So, first the vhost-user-scsi controller, it's going to pull for new I/O requests. Once it finds a request, it's going to build the data structures, and it's going to send it down the stack, and it's going to result in an I/O getting submitted to the NVMe SSD. And at that point, it's done. The vhost-scsi poller is not responsible for checking for any of the completions. That responsibility goes to the BDEV NVMe poller. So when this poller run, it's going to basically be checking these queue pairs to see if there's been completion entries posted. Once it does, there's a callback that was registered with that I/O. It's going to invoke that callback. It's going to go back up the stack, and then the vhost-user-scsi poller is going to, basically notify the VM that its entry is completed. Okay, so now we start to get into some of the, a little bit of the drawbacks of user space implementation. So one of the big things is you want to share SSDs in user space, right? Typically, you're not going to take an SSD and just assign it to one VM. If you were going to do that, probably just doing direct assignment is probably going to be a more effective strategy. So what about SRIOV? The NVMe specification, they recently added, I think it's in the 1.3 version, so it's been formalized how you do SRIOV with NVMe SSDs, but they're really not out there today. There may be some, I'm not aware of any, but it's not really common out there today. And you know, another thing is if you want to start doing features like snapshots, that's pretty hard to do, you know, in hardware with SRIOV. So that's another drawback there. So then what about LVM? Well, LVM's great, but it's in the kernel and we're doing everything in user space. So trying to get a Linux kernel, you know, piece to work with a user space block driver is challenging at best. So next I'm going to talk a little bit about what we're trying to do to provide some of the similar functionality with SPDK in a user space context. Okay, so first, Blobstore. So what Blobstore basically is, it's a user space block allocator. And you know, as we started getting into SPDK, when we started out, it was, you know, basically an NVMe. It was very block oriented, right? It was iSCSI, it was NVMe over fabrics, NVMe pulled mode drivers. But we started seeing cases where people wanted to have some like lightweight file system type operations or even things like logical volumes. And so this is really dedicated for that. This is not meant to be a replacement for you know, a full-blown, fully featured kernel file system. It's minimalistic for some of these use cases. I'm going to get into logical volumes in a minute, but for, you know, for RocksDB, for those that aren't, you know, familiar with it, it's a log-structured merge tree key value store implementation. And so these types of implementations have, you know, typically just a few hundred files, are fairly large, append only, so you can do a simpler implementation of that compared to doing a full-blown file system. And so really Blobstore is sort of the base. It's really focused around just block allocation, just the basics to enable some higher order applications to run on top of it. And then it's really designed for fast storage media. So this has really been designed from the ground up with NVMe in mind. This is not designed to run on, you know, hard disks. It's really focused on flash. So Blobstore design at a high level. Basically, we end up with a bunch of things that we call blobs, and they're basically allocated in clusters. The clusters are going to be fairly large, by default 1 megabyte, but it can be adjusted. There's no naming here. It's all based on IDs. Any naming is done at a higher level. And again, it's completely asynchronous. So everything, it's non-blocking. There's no queuing. There's no waiting. You do a read or write operation. You're passing a callback function and a callback argument, and you're going to get called back once that operation is complete. And it's fully parallel, so there's no locks in the I/O path. And then we rely on the atomicity guarantees that you get like with NVM Express. So NVM Express guarantees at least 4K write atomicity, so that's really baked into the design of how we do the metadata. So we don't have like a metadata journal. Metadata is always updated on a 4K, you know, basis. We do have support for cases where it has to span across multiple pages, and then we basically just have chain pointers so that we can still guarantee that kind of atomicity. Okay, so next, logical volumes. So if you remember back on the first slide, you know, kind of showed how, you know, the stack looked, and it basically just started with this, you know, the BDEV NVMe talking to the NVMe SSD, and now you can see on top of that we have the Blobstore and the logical volume store. So really the more common use case with SPDK vhost-user-scsi is the VM's going to be attached to a logical volume, not the NVMe SSD. So logical volume implementation is basically just UUID XAdders. We have some limited XAdder support with SPDK. So we have UUID on the logical volume store and the LVOLs. You know, we provide friendly names similar to kind of like what LVM does, so that we can guarantee uniqueness within the logical volume store and the application. And then in the future, currently we don't support it, but it actually be not too difficult to add snapshot support, so that's something that the community is looking at adding here in the future. Okay, so next, I'm going to talk a little bit about some of the vhost performance. So basically what we took here was a dual Xeon, the kind of the latest and greatest Skylake-based processors. Basically, we're taking 46 cores for the VMs, and we're taking 10 cores that are going to be dedicated for this vhost application. And this benchmark is really kind of to try to show, what's the maximum performance that we can get here. Some of the workloads, it's maybe not what you're typically going to see from a VM, but it's really meant to sort of demonstrate some of the efficiency improvements that you can get with this kind of solution.
There's a question.
Oh, sorry.
When you count cores, you count virtio-scsi, how threads, or just real cores?
Okay, so the question was, is it counting like hyperthreads, or is it just counting the physical cores? So this here, basically we have hyperthreading disabled, so we're just running with just the physical cores. There's 28 physical cores per socket. Okay, and then I don't know how many people are familiar. I mean, I'm sure everybody's heard about 3D Crosspoint, and so we were actually able to get a whole bunch of the Optane SSDs to put in here. From an efficiency perspective and throughput, you get about the same number of IOPS per second from an Optane SSD as you get from a NAND SSD. But I'm going to be talking a little bit about some of the latency overhead, and that's where Optane really shines, and that's why we chose that for this configuration. And so basically we're putting a logical volume store, an LVM, LV group on each of these SSDs. And then we've got basically one VM on each of these 46 other cores. They've each got a logical volume. So effectively, we end up with 2 VMs talking to each SSD. Okay, so first showing the some of the performance. So the first one here is basically IOs per second. So this is a comparison of SPDK with Linux kernel vhost-user-scsi. I don't have the Qemu comparison with this system. Typically what we've seen is that from a throughput perspective, Qemu, the backend is actually a little bit less efficient than Linux vhost-user-scsi. I don't have that for this configuration, unfortunately. But what you can see here is with this configuration, we get around 2 million IOs per second with those 10 cores using the Linux kernel target, where it's somewhere in the 7.5 to 8 million range for SPDK. But the big one, and I think this is really where this kind of solution shines, is when you start looking at QDepth1 latency. So the Optane SSDs can get the media itself, if you take the software driver overhead out of the picture, is somewhere in the 6.5 to 7 microsecond range. And then the drivers typically, a host driver is going to add maybe 3 to 4 microseconds on top of that. So if this is just on the host, you're talking about 10 microseconds. And so now we're talking about what does it look like when it gets virtualized, plus going through a logical volume type stack. So for Linux and for Qemu, we're looking in the 30 to 40 microsecond range, fully virtualized, where with SPDK it's around 14 microseconds. And so really the big advantages here are a number of things which Felipe alluded to earlier. So one, since we're polling, we don't have any VM exits on the IO submission path, so we can notify the guest VM that he doesn't have to notify us when he submits an IO. We're polling on it, and so we avoid that VM exit. Unfortunately, the guest is not polling, so we still have to send the interrupt back to the guest. And actually, in some of the benchmarks we've been doing, that actually ends up consuming 35 to 40% of the CPU on these 10 cores that's running SPDK. And then on the NVMe side as well, so we're avoiding that 3 to 5 microsecond overhead. It's typically more about 500 nanoseconds for SPDK as far as the submission and the completion path, the cost of doing a single IO. Okay, so future. So there's been a number of mentions of this already, supporting vhost user blocks. So there's some patches on the mailing list right now that are getting reviewed from one of my colleagues at Intel. Live migration. So Felipe, mentioned this earlier. Our focus so far has been on like ephemeral storage. Live migration is going to be a big piece. We have SPDK support for doing like NVMe over fabrics. We don't have an iSCSI driver yet. That's kind of on our roadmap. I think it's something that we're going to be looking at. So live migration with SPDK I think is going to be an interesting use case, and that's something that we're going to want to focus on. And then being able to do logical volume snapshots, so to be able to provide some of those, higher order services that you get from, doing things in the Linux kernel. That is it's one of the downsides with this solution is that when you're doing things in user space, all the things you get with the kernel, they're not there anymore, right? You don't get IO stat, you don't get all these other things, and so, that's one of the things. That's one of the things that we're looking at is, prioritizing what are those things that we need to add to provide as much feature parity as we can. So finally, if you're interested, here's where you can get more information about SPDK. You can go out to GitHub. Garrett Hub is where we do all of our code reviews, and we've got all of our CI feedback. And if you're on there and you've got questions, pop on IRC. We actually have there's people in the SPDK community in Shanghai, Poland, and the US. So typically there's somebody on there 24 hours a day. And with that, we'll take questions.
It's been a really good presentation. Either we explained everything or they didn't understand anything.
We have a question here.
I work in sustaining engineering, which is like basically getting everything that is done and supporting, right? So what I'm seeing on changes like this is that final users are not getting the aspect of pinning things. And what you said about putting everything in an external process and relying on vhost-user, for example, it's awesome if you ping the process that is responsible for doing the backend that the vhost would be doing in the kernel, right? So my question to you is that when you release things like this, is advertised that you are supposed to be pinning the userland process in such ways to guarantee the performance you are seeing in a benchmark, Because if you release this, the final user would put this together with a bunch of vCPU threads, and they would compete, and a mess would be created, right? So you see my point?
No, I do. Yeah. What's that? Yeah, so that's a great, so that's, we have, we have some guides with SPDK on how to do this, and a lot of it can be based on, it's hard to automatically figure out how many you need to do, and so there is some amount of user configuration, understanding your workload and what you need to do, but you're right, these need to be pinned. You need to understand what's running on your system, and so that you don't have this, because swapping out the SPDK thread for something else, that's going to be really bad. Yeah, that's a good point.
Thank you.
Hi, so I had just one question. You mentioned that the guest itself is not polling for completions. So I think that Linux now has the block MQ poll feature in the multi-queue block layer. Have you tried that, or do you think that will help?
It certainly will. So we actually, you probably missed it, but when I had that big eye chart of all the blocks, so we've actually, one of the things that we're working on right now is a virtio-scsi poll mode driver that you could run in the guest. And so we've already done tests where, we can, within our guest, we can check if the interrupt flag is cleared, and then we won't send the guest as well. Now, we haven't done any benchmarking with that yet, but that is something that we should, definitely take a look at to see if, as far as like reducing the late, on both cases, right? Like that should help both on the SPDK side and the kernel vhost-scsi target.
Oh, I have another question. You said that you do not have yet a libvirt integration or something like that. And in the end, users quite often use things like Word Manager or whatever, which basically use libvirt directly or indirectly. Do you have any plans of adding support to libvirt to actually build something like that, or are you aware of any plans?
So that's really a big thing, and I should have put that in the in the future part here, because that's another big part that we want to look at as far as like how do we get this integrated into something like libvirt, because we know that that's how this is typically going to be deployed and used, and so that's something else the community is actively looking at. Yeah.
It's probably gonna, can I borrow that? It's probably gonna look like some sort of plugin interface. So the idea is that if you're writing your own target application, then you write a corresponding libvirt plugin so that libvirt knows how to talk to your application. And in this example, we have this SPDK-based application. we would probably submit this libvirt interface together with plugins so that it knows how to talk to that.
Yeah.
And the key things are things like LUN resize. So if you resize a virtual disk, you have to tell the target application, which is handling those event VQs, to then tell the driver that some LUN has changed, or plug or remove.
Yeah, and then I think the other thing is just looking at, so I think it's really easy to sort of like genericize the SCSI part of this, but then when you want to do things like logical volume management, you know, having the plugins for that too. And so I mean, there's definitely some work there. I think the plugin strategy is good. I think there's just some work to figure out what that API needs to look like to cover as many use cases as we can.
So we welcome
Yes.
people to get involved.
Absolutely. There's a question over here.
And how many CPU should you dedicate for polling to get best performance?
I hate to take the cheap answer, but it depends.
What is your estimate?
Oh, what's that? Yeah, so we've gotten to where, you know, if you're just doing like local ephemeral storage, you know, you can get, you know, effectively 1 million IOPS on, you know, using a single core. Now, if you start doing things
for
like
how many disks or VMs running in parallel?
So it would depend on how many VMs. Well, it could be it could be anywhere from 1 VM to 10. So it's really cheap. This polar strategy, it's very cheap to, you know, whether it's polling 1 or 10, there's very little additional overhead when you're polling more VMs. So part of it kind of depends on, you know, what does your system look like? How many VMs do they have, and what kind of I/O load is each one going to drive? But in a rough scale, it's somewhere on the order of, you know, 800,000 to 1 million IOPS per core. Now, when you start looking at some other protocols, so like let's say you were going to do, you know, iSCSI, and so instead of this, you know, basically proxying VirtIO to a local NVMe device, it was iSCSI instead. iSCSI is going to have more protocol overhead, so you're probably going to need to allocate more cores because it's not going to be able to hit that same IOP level per polling core.
Okay.
Does that answer your question?
Yep. Thanks.
Okay.
I think we're hitting time limit. 1 minute left. Okay, thank you everyone then.
Thank you.